We are trying to pick up from yesterday. I got it. Oh, yeah, no, you're good. And we left off with this example. Question, what is the term that describes what type of sequence this is, or how it is defined? What's the term? For what type of formula this is? Recursive. All right, click along now. So recursive. Okay, this is a recursive formula. And a recursive formula says to find the next term, work with the previous term or the prior term. So, how did I use this recursive formula to find a sub 2?
Well, you took the 2, since 2 is equal to k.
Good.
You're like, hey, k minus 1. Oh, we're using a1. But boom, bada bing.
Good. So, since a2 is this one, I need to take, for this one, I need to take the 1 less than term. I need to go 1 term back. So if I'm trying to find a sub 2, then I use a sub 1. And what do I do to a sub 1? Times negative 2, multiplied by negative 2. So therefore, what do you guys do in order to find a sub 3? Was I using a thinner marker today? Or yesterday? Even a thinner marker? Okay, a sub 3. What do I do? Use a sub 2. So I'm going to have negative 2 times a sub 2, and a sub 2 is going to be? Oh, we can find that. There you go. Because we have negative 2 times what was the term before, negative 28, which ends up being negative, what was it? Ah, good, positive 56. To find the fourth term, you do negative 2 by the previous term, which would be the third term, negative 2 times 56, which would be 112, but with a negative.
Yep.
And then to find the fifth term, do negative 2 times the fourth term equals negative 2 times the negative 112, and we get positive 224. Who got there? But the rest of you guys, does it make sense? Recursive just means jumpity jump jump, and what tells you how to jumpity jump jump? The formula. It says multiply by negative 2, multiply by negative 2, multiply by negative 2. See how it's jumping? So in your formula, in your calculator, for those of you guys that are gone, I had them work on calculators while I was trying to get organized for class. And I said, hey, let's figure out how to put this thing in our calculator, because we talked about how yesterday recursively defining operations or programs or sequences, etc., isn't very practical for us unless we're just trying to find like the 6th term or the 7th term, but to find the 100th term, ew, this is gross. But if we were able to program that and tell a computer to do all that work for us, it can go so much quicker, so much more efficiently, and it can do that jumpity jump 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 pattern. So we went to, in our calculators, the SEQ sequence mode. In sequence mode, y equals, we have this stuff to fill in. Now, we talked about how there is an n in your calculator, and where did you guys figure out that n is lurking? Maybe it's not lurking, maybe it's not that creepy, but where was the n? Look at the variable button. See how sometimes it's an x, now it's an n? Do you guys notice how that corresponds to the modes?
Wow.
Function mode, it's an x. Par mode, now it's a t. Polar mode, guess what? It's going to be a theta. Sequence mode, now it's an n. Whatever mode you're in is whatever variable is going to come out when you push the button. So, let's come back. U of n is very similar to a sub k. U of n is very similar to a sub k. U is like a and n is like k. So, if I want to write this in, do you guys at least figure out the negative 2 times something? But how do I write this guy? Who found the little baby u? Nicole, where did you find the little baby u? If you go second 7, you get the u, like the u for your equation. It's a lot easier than going to bars and y bars for function mode. I have my little baby u. I'm going to say u of, not k minus 1, u of n minus 1, which is like k minus 1. 2, and then to find the n, you hit the variable button, right? And then if you guys want to double check the beginning, remember how yesterday I said you can hit second back and it goes to the beginning of your whole line? You can just second into the very end of your line. Isn't that spiffy? I only found it out like last week. Anyway, so why is there something else though? In function mode, you only have to put in one equation and you're done. How many pieces are there in a recursive formula? 2. There's this one that tells us how to get to the next term, and there's this one that tells us where to start. Hey, wait. Who's n min? 1. So if I plug in n min 1, who's u of 1? Who's a of 1? Who's the first a? 14. We put that information right there. Do you see it? Now, why is this so spiffy? Remember how we can go to a table and it can generate stuff for us? Uh-oh, I have no idea what I plugged into my table. That's why it took forever. You can always clear out, delete out whatever was in there before. Okay, now it's all clear. The first term, what should it be? 14. Second term, -28. Third term, fourth term, fifth term. Okay, so the calculator can do what I did. Is that really all that snazzy? No. Well, what is snazzy? Can we ask it for the 10th term? How about the 20th term? Ooh, that was pretty fast. A lot faster than I would have done 19 jumps, right? Do you see how big this number is, though? We might get in trouble soon because there's only so much that can fit. I might have to go in overflow, meaning the calculator's like, it's too big for me to handle. Because e to the 6, guys, scientific notation, what does that mean?
That's to the right.
To the right 6 places, right? We can try 30. Oh, it's still working. If we go 40, it might be a little too intense. Oh, it's still working. What if we go 100? We're going to go for it? Ooh, look! What did it just do? It jumped how many times? 99 in that little split second. Now, guys, maybe you'll see, though, how hard this poor little calculator is working when we type in 1,000. Ooh. It's having to make 999 overflow. It was too big. It was too big. So it's jumping. The long story short is it cannot fit in this little window how big the number is because the e is so big. Does that make sense? The scientific notation that has too many zeros following it. But if you were to go to like a normal computer, I bet it could do that. Anyway, cool beans. It does what we don't want to do. Now, why do I have over here the most famous recursive sequence? What am I talking about? Who is this Fibonacci sequence? What does this Fibonacci sequence do? How was it found? Had something to do with bunnies and how quickly they reproduce. Has anybody ever raised bunnies? Ever had a friend that had bunnies in the backyard?
Yes.
They have multiple bunnies?
She was so mean. She used to clean them up by the ears. Yeah, that's how yours.
That's how yours is.
That's me.
Question! How quickly, if you have a couple bunnies, how quickly do they make more bunnies if one's a guy and one's a girl?
Real quick.
Real quick. real quick. Because they're like going to adult, be able to make babies time is really quick. So here's a long story short. Someone figured out this quickness. Ready?
Why would Fibonacci
And we're kind of glad he did, and here's the reason why. Ready? Let's say, okay. Let's say you have a pair of bunnies. Hold on a second. Yeah. You have a pair of bunnies.
I thought you were going to actually draw.
Hold on. We'll say we have a female bunny. Does that make sense? There's a male, but we're not talking about the male. Okay. Let's say we have a female bunny. Okay. And the bunny's born. Cool. Within a certain amount of time, I think it's like 3 months. It might be even shorter though. Within a certain amount of time, anyway, after 3 months, said bunny is ready to reproduce, aka couldn't before. So after 3 months, bunny's still there. Bunny now months, but now there's another baby bunny. Okay? Said baby bunny has 3 months until it's able to reproduce. Well, we're talking about girls. And then this bunny is able to stay and remain, but then also can have another bunny. Okay? This one all of a sudden can stay, but now this bunny can reproduce. This bunny is staying and reproducing. This bunny is still trying to mature. Now, this bunny is staying and reproducing. This bunny is able to stay and reproduce. This bunny is maturing. This bunny has matured, so now he's able to have a bunny. Oh, sorry, that's awkward. What's going on with the numbers in said picture? How many bunnies do I have for the first one? 1. How about the second one? 1. How about the third one? 2. How about the next one? 3. How about the next one? 5. How about the next one? 8. How about the next one? Guess how many bunnies are going to be? 13. After that, 21. After that, 34. Wait, how does this sequence work?
You add them together.
Add what together?
The previous, so.
The previous 2 terms, right? Then the previous 2 terms, and then the previous 2 terms, right? Now that gets really confusing when I'm drawing arrows. So we can say 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc., etc., etc. Now, question, how could I make a recursive a recursive sequence that defines how this sequence works? What does this sequence start with? Just 1? Some people say 0 and 1. The better way of looking at it is probably it starts with 1 and 1. What? Because in order to do the pattern, don't you need 2 terms? So we'll say it starts with 2 terms. We'll say it has an A1 and an A2, but our calculator can't handle that, so I'm just saying A1 is 2 different things, 1 and 1. How do I get to the next term? Add what together, though? How could I write it recursively? How can I talk about the previous term? It's A sub somebody and A sub somebody. Last one. How did I talk about the previous term back here? K minus 1, right? Take the placement and then take away 1 from the placement. So question, how can I talk about the previous term? K minus 1. Take your position, go back 1. But do I just go back 1? No. If I was trying to find A sub 3, I would need to go back and add A sub 1 plus A sub 2, right? So this would get me A sub 2. How do I get A sub 1? How do I go 2 places back? K minus 2. Let's see if we get Fibonacci in our calculator. Let's see. Any ideas? How would we put this up here? I'm going to first clear out my table because sometimes these big numbers, oh, that's not a table, that's a graph. Sometimes these big numbers can kind of mess up when I put it in a new sequence. So let's delete. Recursive formulas don't have to just be built on 1 previous term. Sometimes they're built on 2 previous terms. So n min is 1. Can I try to make my first 2 terms 1 and 1? Let's see if, oh, that's not going to like me. What else can I do? Maybe we just need to like input 1. Let's see if we can now add 1. Is it happy now? Ooh. Okay, maybe. How can we talk about this? Who is A the same thing as in your calculator? U. So we're going to do our second 7. We're going to do U of, who's the same thing as K? N. So we're going to do N minus 1 plus U the first term? Second term. Third term. Ooh. Fourth term. Fifth term. Sixth term. What do you guys think? Is it working? Now, what's something else that's cool about the Fibonacci sequence? It's also called the Fibonacci spiral. Spiral. I don't get it. What if we do a little 1 by 1 square? That's 1. What if we do another 1 by 1 square? That's 1. What if we then say, hey, that's a side of 2. Let's make it 2 by 2 square. That's 2. 1, 1, 2. What if we then say, hey, we can make another square building off of that, and now it's a 3 by 3. So we have 1, 1, 2, 3. Now we can add that 3 to the other remaining 2, and now we have a 5 by 5. We can add that 5, which is here, to the 1, which is here, to the 2, which is here, and that's going to make an 8 by 8. We can now do the 8 plus the 2 plus the, what was this one? 3, which is going to end up being 13 by 13. We can do it again with all the other remaining ones, and we're going to end up with 13 plus 8 is going to be 21. Now, why is this so spiffy, and why is it called a spiral? If you were to start right here in the inwards, and if you were to go through each of their diagonals, what do you guys notice? What I was able to do is perfectly a little bit better. What are things in nature spiral? Any idea? What's something that spirals in nature? Yeah, they actually turn, but what has a spiral? Snails, snail shells. Snail shells, the spiral is proportional with the Fibonacci spiral. What else? Nautilus shells? Is the nautilus shell like the cross section of the inside? Spirals. You guys ever seen a branch with like different buds on it? The spiral of how those flowers bud on the branch actually fits in the Fibonacci spiral.
Oh, yeah.
If you were to look in like a sunflower, and if you were to see in the middle of the sunflower the way the seeds are distributed, actually those spiral according to the Fibonacci spiral as well. There's actually tons and tons and tons of things in nature that display the Fibonacci spiral. 1, 1, 2, 3, 5, 8, 13, 21, etc. Maybe someday we'll watch a really cool video on it. There's this lady called Byheart. She's actually, I don't know, I guess I should call her a lady by now. She's grown up, but she has a really cool perspective on it. For today, we have to kind of keep going to see how far, I think it's a calendar, we need to go. However, this thing called Fibonacci is a lot bigger than you might imagine. Let's keep going for right now. We gotta get through section 9.1. Factorials. It's not just n. What is it?
It's very loud then.
0. No, that's not it. What's factorial mean? It's the product of all the previous. What kinds of numbers are those? 1, 2, 3, 4? Integers. Good. All the previous integers starting from 1, ending at the number whose factorial you're talking about or referring to. Now, this one is counting up 1 times 2 times 3 times 4 all the way up to n. Usually, we kind of think about it more counting backwards in the sense of 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. In your calculator, calculatrice, calculadora, where is that little factorial hiding? Anyone remember? He's hiding somewhere. We would guess math, right? And I already heard someone say probability. There he is. Little baby factorial, number 4. probability? I think we're building up to something, and you're right. Special type of product is a factorial. Now, we're not going to go into all the details of a factorial, all the applications of a factorial today, but we will just work with the basics, just making sure you know how to play with them. For instance, this little guy, for right now, let's just memorize 0 factorial is equal to 1. Really? Kind of like anything to the 0 power is. That's one way I remember it. Anything to the 0 power is 1, 0 factorial is 1. Similar in the sense of how to memorize. And if I was to give you numbers like, I don't know, 7 factorial, or 5 factorial, or 3 factorial, you would just say 7 times 6 times ... times all the way down to 1, right? 5 factorial, 5 times 4 times all the way down to 1, right? But what if I was to give you something like 2n factorial? First of all, is there a difference?
Yes.
Yeah. So what do we rewrite the top one first as 2 times n factorial? Right? So we would go ahead and write this if you want to in the terms kind of the one up above. We could write it 1 times 2 times 3 because we don't know how big n is. That's one reason why. Maybe we start at 1 and count up. But what would be different in the bottom one? What if there was a parenthesis around the 2 and the n? Where does that show up? This one, they show up separately. Before you do the factorial, exactly. So, I'm just going to start, and when am I going to end? Does that make sense? Now, it's starting to get weird. Factorials are kind of hard to grasp anyway. When you start putting variables in, it gets kind of even weirder. But 2 times n factorial, just think no parentheses. PEMDAS, think the factorial comes before the multiplication. So factorial we can kind of put together with the grouping symbols or like with the exponents if you want to think about like order of operations. So the factorial happens first, then times 2. As in the bottom one, it's just like, oh, that is the factorial, so I'm going to end at 2n instead. Why is this useful? Well, we might be having to actually plug in some stuff. And if we plug in some stuff for sequences, factorials might show up. And there's a reason why. Because our work with sequences is foundational. We're not like getting a full grasp of sequences and what they're used for, how they're applied. It's foundational. So we're just seeing, okay, can we work with sequences? Can we figure out what's going on? And what if they start throwing factorials in there? Okay, kiddos, how will we find the first 5 terms of this sequence? Nice thing is, real quick, it's defined explicitly, not recursively, so all we have to do is plug it in, plug it in, plug in what? N. So how can I find the first 5 terms? I find A1, plugging in, N is 1. Find A2, plugging in, N is 2. Find A3, plugging in, A is 3. Find A4, plugging in, A is 4. Find A5, plugging in, A is 5. Oh, come on, plug and chug. You guys got this. Ready, set, go. Plug and chug. People in the back, can put it up just a little bit. I didn't realize the window got down. There you go. What'd you guys get when you plugged in 1? Careful. Oh, sorry. I apologize. You're supposed to start at 0. Did anybody notice that? Epic fail. That's okay though. What can I do? I know I'm cheating, but I have an electronic device. However, I put a little ace of 0 first. Aha. So then we technically will stop at the 4th. Or I should say when n equals 4 is technically the 5th. So, plugging in 0, yes, now you're right. Anything to the 0 power is 1 and 0 factorial is 1. So 1 over 1 is just 1. Plugging in 1, 2 to the 1, over 1 factorial. 2 to the 1 is 2. What's 1 factorial? Also 1. Good job. Also 1. Alright. Plugging in 2 squared over 2 factorial, which is 4 over 2 times 1. 4 over 2 is? Oh, that's weird. Plugging in 3, I get 2 cubed. All over 3 factorial. 2 cubed is 8. 3 times 2 times 1 is 6. And 8 over 6 is 4 over 3. This is one weird sequence. Went up for a little bit, stayed the same, and now it's going down. Plugging in 4. 2 to the 4th over 4 factorial. 2 to the 4th is 4 times 4 is 16. All over 4 times 3 times 2 times 1, or 4 times 6, 24. 16 over 24, 4 over 6, better than that. 16 over 24 is 2 over 3. So this sequence, 1, 2, 2, 4 thirds, 2 thirds, and we can keep on going, but they just said find the first 5. They just said find the first 5. So we got to play with factorials just a little bit. Could factorial stuff get a little more exciting? Sure, maybe. Let's go check it out. Woo-hoo-hoo. What if they say, instead of just plugging in and solving for factorials, what if they say simplifying factorials? Oh, no big deal. Let's just multiply. 8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times, 1. Get that big old number. And let's figure out what 5 times, 4 times, 3 times, 2 times 1 is. Get that number, then let's reduce. Or,
I know.
Can we just do
yeah,
that?
see it?
5 to 1.
Can we just say, forget all those guys, it's just 8 times 7 times 6? Which would be 56 times 6? Which would be 6 and 3, 336, I think.
Yeah, that's right.
Now, how can we use something cool like that to help us with letter B? We can't factor with factorials, sadly. You think you would, right? Remember how n factorials we count up instead? Because we don't know who n is, we don't exactly know how to count down. If we count up on the bottom, what are we going to do on the top? Count up. The question, where do we stop on the top? N minus 2. Well, how did those two compare? Question, what would have been before the n? N minus 1. If it's 10, it would have been 9. If it's 56, it would have been 55. If it was 72, it would have been 71. N minus 1. Question, what's 2 behind n? So now what can we do? Reduce and say 1 over n minus 1 times n. Weird, but it's a whole lot easier to work with algebraically, mathematically than this thing. So if there is ever an expression with factorials top and bottom, we're just trying to get you a little more used to factorials, especially in preparation for probability. Now, hold on, wait, SATs tomorrow for some of you guys. Question, what is this Greek letter? Sigma. Series. 9-1 introduces us to all sorts of stuff. Sequences, A1, comma, A2, comma, A3, comma. Never mind. So, series, A1 plus, A2 plus, A3 plus. Series are one big sum of the terms in a sequence. And that can be shortened, that can be simplified, this big whole sum of who knows how many terms in a sequence can be shortened using this cool sigma notation, also known as summation notation. We'll just say a summation. Using the Greek letter sigma. So what does this notation mean? Do you guys see the one that we started with? What's the bottom bound? Ooh, snazzy. What's the bottom bound of the sigma? The 1. What's the subscript that we end with? N. And what's the upper bound of the sigma? N. What's the formula that we're plugging into all along the way? A's. Summations, sigma notations, a way to shorten or to simplify. Repeated addition. Now guys, there are some properties and whatnot, but with the SAT, the properties, you can see them in your book if you need to use them. I'm not going to have you guys necessarily write them down right now. Maybe you'll need them in homework, maybe you won't. Can I just have you guys do an example and see if you know how to do a summation, just as we end today? Which this is going to be the end of 9.1. And this page, well, we're going to be working on him for quite a long time. He's just the introduction of something that we're going to work with a whole lot more in chapter 12. Letter A. So, I'm repeating some addition. But what am I repeating? Where do I plug in first? Plug in the 1. So to find a sub 1, I plug in 1 to whatever I is. He's not imaginary. He's just an index. He's just a variable standing for what to plug in. But I don't stop at 1. I count up by integers until I get to 5. So what am I going to plug in next? What am I going to plug in next? Kind of like a factorial. It counts up. I'm not multiplying, but I'm counting up. Now this is cool. I wonder if my calculator can do something like this. Math menu. Now, this is a little sad for those of you who don't have the updated. If you have the yellow button, you're going to be really sad. You don't have anything that can do this, at least not quite as simply, and it's much more complicated. It's easier just to do it like this in your calculator. But those of you guys that have this thingamabob, that's fun. And instead of using I, because it takes too much time to do alpha I, can't we do like an X, and then can't we? Oh, it says alpha, doesn't it? We'll do alpha A just because it's the first one we find. We could go from 1, and we could go all the way up to 5. And we could say something like 3 times now. Whoever you put in this little guy, just use the same dude here. Alpha A, for instance. Guess what it's going to do? Solve. And guess what that equals? 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Because you have 1, 3, 6, 10, 15 threes. And 15 threes is the same thing as 45. Now, to get a little bit spiffier in the sense of your expression could get a little more complicated, like 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared. We can still, people with yellow buttons on your calculator, you can still just plug that in and have it do it for you, right? Or a mental method. But if you know where this little feature is in your calculator, that's kind of good too. Do you have to use A? Nope. You could use K. You could use I, but I didn't want to find wherever I was in there hiding somewhere. Kids, the only thing that we didn't get to talk about in much detail is what happens when you go to. Ooh, don't worry. That's just, yeah, we'll talk about him much more in